Okay, so this is just an overall chem of Unit 1. Credentials, second time taking AP Chem. It's whatever. So basically, mole is 6.022 times 10 to the 23. It's used as a counting unit, and it can be 6.022 times 10 to the 23 moles, atoms, ions, or formula units, depending on what you're measuring or depending on what the question is asking. Okay. So how many atoms are in 3.02 moles? So essentially, you want to put 3 moles on top of O2 and find how many atoms. But so you have to know 1 mole of anything is 6.022 times 10 to the 23. So over 1 mole is 6.022 times 10 to the 23. And essentially, that just equals 1.81 times 10 to the 24 if you use your calculator, atoms. Next question. How many moles are in 9.03 times 10 to the 23 molecules of CO2? So first, we're going to work backwards. So there's 9.03 times 1023. And so you need to go from molecules to moles. So 1 molecule, essentially, like I said, for units, is just 6.022 times 10 to the 23. Over 1 mole. And just using your calculator, that's equal to around 1.5 moles. But you want to be exact because this is a 3 sig figs, so you want this one to be 3 sig figs as well. Okay, next question. How many moles are in 18 grams of hydrogen? So, or how many molecules? 18 grams of water, H2O. I don't know, I'm tweaking. And convert to molecules, but first you have to convert grams to moles. So 1 mole, or so 1, so sorry, I tweaked out. So it's 18 grams of H2O for every 1 mole. And then you're going to times that 1 mole of H2O to 1 mole here. And 1 mole over 6.022 times 10 to the 23. So essentially, just 6.022 times 10 to the 23 is your answer. Okay, next question. How many molecules are in 44 grams of CO2? Same thing. So how many grams are in CO2? So you have to do C is 12, O is 16 times 2. That equals 44. And so 1 mole over 44 grams of CO2, you cross the grams out, obviously. 1 mole is equivalent to 6.022 times 10 to the 23 molecules. So essentially, it's just 6.022 is your answer. Okay, that sounds good. Okay. Hold up. Mass spectrometry. So it just separates isotopes according to mass. Really, it's just about calculating, nothing too much conceptually, as long as you really understand. So it's just also used to find relative abundance and mass of unknown samples. So it just goes through stages: ionization, acceleration, deflection, detection, and you kind of need to know this, but not really. So because some parts Miss Corbett asked is conceptual, so it just really depends. So we're gonna go back to the worksheets. Naturally occurring bromine, and look, mass is 158, 160, 162, and their relative abundance is that. So you need to take those relative abundance and turn it into decimal form. So it'd be, and you need to multiply the decimal form according to their masses. So 158 and then you're going to add them all together. And this all equals 159.96 AMU. So that's your answer. And then an unknown element is used, and they just want you to graph it out. So, it's easy. It's just this. This is your isotope. So it's gonna be Z50, Z52, Z53, and then Z54. And so since Z50 is the smallest, it's going to be out of 100, so you're just going to graph it like this. Z52 is one of the highest. It's going to go up there. Z53 is smaller. Then Z54 is the smallest. So essentially that's it, but make sure to label the relative abundance. Calculate the average atomic mass of Z. So this is from the also connecting to part B. So essentially it's the same thing. Z of 50, you're going to do the isotope number times the relative abundance in decimal form. So 0.0434 plus 52, 0.8379 plus 53, 0.0950 plus 54 times 0.0237. And once you multiply and add them all up, you get 52.0556 AMU. And then you need to identify the element. Just go in the periodic table and then look for it there. Okay. And then we're going to empirical formula. It's just the simplest whole number ratio in atoms, or of an atom in a compound. So, it's pretty simple, and this is just review, so I'm not trying to teach you anything new. It's just going over basic concepts and what Miss Corbett may ask you. So, assuming everything will equal 100, C is 40, and you won't have to divide it. Convert all of it into moles. Okay, so we need to divide this all by the smallest, so we at least have a whole number. So divide by 3.33. And that just equals 1, and that just equals 2. So it's just CH2O. However, if it asked for this is equal to, if it asks for, like, let's say CHO equals like this amount of grams, find the empirical formula from the molecular. You have to divide molecular by empirical and times the empirical by the number you get. If that's complicated, just ask me. Compound. Okay, so it's just 25.6 8.9 divided by 14.01 of nitrogen and 74.1 divided by 16. Divide by the smallest number. So N should equal 1. And then O should be equal to around 2.5. But since this is around 2.5, you need to times it by 2. And you need to times N by 2. So it's just going to be N2O5. Okay. So this is electron configuration in the PEZ graph. So electron configuration essentially is just how electrons are arranged. And it just goes by specific orbitals, S, P, D, F. And there's a graph on the top right. You should know the principles where it always fills up the lowest energy orbitals first, and each orbital holds 2 electrons max. And then electron fill orbitals singly first. So it's just I'll draw it later. So essentially, configuration of sulfur, you have to go from the chart 1s2, 2p, 2s2, 2p6, 3s2, 3p4. And to make sure you did it right, just count all the electrons here, and if it equals 16, then you get the right amount. It's just basically following a pattern. Which atom has this? So we didn't know that neon is essentially the number 10. And that means it has 10 electrons and 10 protons of whatever. So 10 plus 2, 5 equals 17. If you look down on the periodic table, that'd be chlorine. Why is it chromium this instead of 4s2 and 4s1? This is actually because it's more stable when it is like this. Because it's hard to explain essentially, but the d orbitals will be more stable when it has an electron right here rather than there. And let's say it's asking like Cr2+. You should know that you need to take electrons from the most outer orbital, which is 4, not 3. Because it's just something you need to know. Like, you take it from the most outer orbital when there's a charge to it, positive or negative. So photoelectron spectroph, whatever is experiment technique, it just shows measuring like the ejected electrons and just binding. So for oxygen, each of these little nudges or spikes represents the orbitals, like S or SPDF. So one peak is for 2 electrons. If you can see, like, there's 2 lines there. And then there's another peak for 2s, an even larger peak for 2p, and so on and so forth. This is not the right one, I believe, but yeah. Oh, actually it is, sorry. It's just this one's kind of messed up. Anyways, periodic trends, this is probably the most important one you need to know. So it goes from atomic radius, going across a period, it decreases because more protons equals greater nuclear charge, pulling electrons in tighter. So basically, the more you go across a period, there's more electrons in an element, and there's more protons in an element, which means that the electrons will be stronger, since the protons are making the electrons like squeeze in together in like greater charge. However, if it goes down a group, it'll increase because since there's more electrons when you go down because the number gets bigger, there's also more electrons and more shells, which means the rings of like an element, like this, there will be more rings here. And when there's more rings like that, it'll be easier to pluck off an electron from this ring rather from here because this electron from here is closer to the nucleus than this one. And then for ionization energy, it's energy required to move an electron. So when you're going across a period, it'll increase because since there's more protons when you're going across the period, there's going to be more charge to it. So when there's or more like electron like stronger nuclear charge and stuff. So basically what I'm saying is more protons equals greater pull or greater attraction because I'm trying to think. More protons means it's essentially smaller as well because more protons just equals smaller atom, and also more protons equals more ionization energy because it's so attracted to the nucleus. However, when you go down a group, it'll be easier to remove because essentially the same thing. More electrons means more shells, so more shells means it's easier to pluck off from the outer shells because it's not as attracted to the nucleus. Electronegativity is just the ability to bond to another electron. So when you go across a period, it's the same as ionization energy, because nonmetals want electrons because if you look here in the periodic table, fluorine is the closest to like neon, and fluorine really wants that electron to be stable. So like the more like you go down, the more it's like less likely to be wanting to be a stable gas. Along here, it's just not wanting to bond as much compared when you're going up and to the right because going back from here, it just mainly because like fluorine wants to be like an electron, or it wants to be a noble gas, wants to be stable, and it just surrounding it, like the elements surrounding it, will slowly decrease as like it goes away from fluorine, essentially. Electron affinity is a little different because it's just like saying like the energy charge when an atom gains or removes an electron. So it's the same thing as electronegativity because essentially it's the same, like it all comes down to protons, or yeah, essentially that. So when you go here, it's because fluorine wants to, as I said before, fluorine wants to be connected to neon, or wants that extra charge or extra electron actually to be stable. And the thing is though, it becomes more negative / favorable, but when it goes down it becomes less negative, less favorable, because when you're going down like this, wrong one. When you go down, the electrons are like slowly not disassociating, but slowly having less attraction towards the ones in the proton, essentially. So in general, this is the largest atomic radii, while this is essentially the smallest. However, since this also has the greatest ionization, electron affinity, and electronegativity, meaning it wants to be stable. It'll also be one of the hardest to remove and is also one of the smallest due to protons and all that stuff. However, when it's asking, like, let's say, like, it's like F minus and O2 minus. And because F is 9 electrons, but it has a minus, so that means it'll be 10 electrons. O2 is 8, but since we have 2, it'll also be 10 electrons. Miss Corbett will usually ask why, like, which is smaller in terms of, like, or explain why which one is smaller or / which one is bigger. But the thing is, these two have the same electrons, so how would we know? Actually, we would know because this one has 9 protons and this one has 8 protons. As I said before, more protons equals smaller, which means F would be considered smallest due to the amount of protons compared to oxygen. But yeah, that's like basically it. I'll add more if I think of anything.